Let's move on to the last talk of this session by Mattia Bergomi. Mattia, you ready?
Yes, wait, I'll stop sharing.
Yes, I am. Let me just share my screen.
So he will tell us about comparing neural networks via generalized persistence.
Yes. Are you seeing my screen?
It's black right now. Now it came.
Okay, yes. That's great. I'm sorry, I'm going to stop my video just because my connection is utterly unstable today. So first of all, I'd really like to thank the organizer for inviting me, and of course all of you for bearing me with my talk on this at this time, right? We're close to lunchtime here and probably dinner time in Singapore. And what I would like to do today is to tell you about a line of research that may be somewhat collateral to my last activities that are more at the interface of machine learning and functional analysis. But still, this work started in 2016. So for this reason, I will start by telling you about the main characters of this research, the team, our motivations, internal motivations and aims. And thereafter, I will sketch for you the theoretical framework that we developed and give you some example that will lead us to a third part in which instead we provide some direct application of the framework. So let's start with our team. So my journey in generalizing persistence started in 2016, as I told you, in Marseille, where Massimo Ferri told me that he believed it was possible to build meaningful persistence-based representation, let's say persistence diagrams, directly on graphs. And obviously, I did not believe him. That until Lorenzo Zuffi started his master thesis with us in 2017. And indeed, he studied, the state of the art of construction, simplicial construction on graphs. And then indeed, we found some direct applications. And later on, Pietro Vertechi, during his PhD, joined us and put his categorical knowledge on the table. And indeed, we managed to build the framework that I'm going to present to you. And Antonella Travaglione and Alessandro Mella developed some application of this framework that I'm not going to speak about today, but I believe Massimo is going to show you tomorrow. So, motivations. We know that many applications deal with data that are not naturally representable as simplicial complexes, as we saw in some previous talks, right? And there exists a variety of constructions that are very, very clever that allows us to map these data into simplicial constructions and then compute persistence. However, it was unclear to me, it was unclear to us, how we could know a priori which kind of information was forgotten or even added by these kind of constructions. I give you this example. Here, you can see how we are building basically from a filtration of a weighted graph. We're building a persistence diagram based on the complex of click computed on the graph or its complement. And you see that modifying only the last step of the filtration, this modification induces a change only in the complex of clicks of the complement and not of the graph itself. So with this, I want to make this very clear. I'm not saying that these constructions are not useful. I'm just saying that sometimes it's very hard to understand how they are affecting the information flow. So our approach was based, well, let's say our theoretical aim was to work on other categories than top and vec and functors that are not necessarily homology, but still making construction that can yield persistent diagram, and that where we find the usual properties. In more practical terms, what we want to do is to deal with objects such as, you know, weighted graphs with a coloring, or, you know, quivers, manifold with group actions, and even closer to those kind of applications that commonly arise in machine learning with labeled point clouds. Obviously, we're not the first ones doing that, and I list here a state-of-the-art, surely incomplete, but somewhat of those papers that I believe are very going into this direction. Our approach started from, I would say, Massimo's intuition that we could look for an axiomatic persistent theory. And so what we did was to start by listing out the fundamental ingredients of persistence. And obviously, one would start with a filtration, well, then a functor, and then needs a measure of rank in the target category, in FinVec in this case. And with this, one can write a sort of, you know, general recipe. So once the recipes was written down, we focused on how to generalize the notion of dimension of a vector space. And what we did was to turn to regular categories. And we did that because, you know, on the one hand, they cover most of the categories we were interested in. And on the other hand, they allow us to define a notion of image. As you can see in the example there, in the category of sets. So we can define a rank function on a regular category, but making sure it respects the inequalities that characterize the dimension and cardinality. And we added that additional requirement on pullbacks that I will briefly explain. So what we want is that when restricting a surjection, the excess of the domain on the codomain is reduced. And in particular, if that happens along fibers, we call that a Fiberwise rank function. Now, we found a lot of examples that seem to us particularly good. So, you know, cardinality in thin set and dimension in vec, but also the length in an abelian category. And, well, any non-negative exact function. But the point is, I'm not the categorist of the group. Pietro is. So for me, it was very important to understand why abelian categories as well. You know, abelian categories, such as, you know, modules on a ring, have, of course, all the properties that we need to build categories. And gracefully, they yield a notion of dimension as length. And what we did afterwards was simply to start building categorical persistence function. And how did we do that? Well, you know, we took the standard properties that we want, and we followed our axiomatic path, and we simply modified this definition by substituting basically commas with arrows, if you want, and so that we could recover the original definition of persistent function for our index diagrams. So if this is the definition, now how can we bring it up a bit all together and understand how we can define these functions? Well, we can define them from a rank that we described before. So if we have a rank function, then the rank of the image of a morphism is a categorical persistent function. And this allows us to retrieve, cardinality of the image when we have a function between sets, the rank of a morphism in VEC, and as we said before, the length of the image of a morphism in an abelian category. We can also build new categorical persistent functions, and we can build categorical persistent functions from others, and we do that simply by factoriality. So this allows us to recover homology, but also to define persistence function, for example, on blocks. Here you see that we restrict ourselves to thin graph monic because we want to guarantee that we have filtrations. So now, what we have in summary so far. I know this is all very, very much of a sketch, but you can find the details in the paper I was referring to before. So if classically persistent Betti numbers and persistent functions are defined on the upper diagonal of R and in pairs with U less or equal than V, categorical persistent functions are defined more abstractly on the morphism category. We can do that, and this is known because the upper diagonal is on one-to-one correspondence with the morphism of our index diagrams, right? So that we can define function on the upper diagonal from a categorical persistent function. We can simply define a functor from the R index diagram to the category, as Francesco, I think, was hinting to that before. It is also we can of course retrieve the fact that in inclusion maps do not need to be monomorphisms, although you saw before in the block case we had to refine ourselves to consider an only monic morphism. So to sum up a bit what we saw so far, our framework compares to the classical one, if you want, in this way. So instead of the topological space, we can consider any arbitrary category C as a source, and instead of vector space, we need a regular category. Instead of the dimension, we use one of our rank functions that I described before, and instead of the homology functor, we can use any functor defined on C to R. And filtration are substituted by our index diagram in C. So what else? We need to define persistence diagrams, right? But we can define persistence diagrams in the usual way. There is no problem about that. There is no problem about their multiplicity. What we see is that indeed we can also define persistence diagram in semi-simple categories. And you see now that we're kind of getting closer to our aim of using our framework in labeled scenarios, for example. What we have is that naturally in semi-simple categories, with rank function length, the persistence diagram is informative about the decomposition of the R index diagram, and we can indeed build a persistence diagram which is basically counting simple objects, with the caveat that we are indeed counting simple objects and we are not distinguishing them. However, we surely can try and go to the directions our aim was to distinguish these objects and not only counting them. So we turned to studying how to measure distances between persistence diagrams, and it will be clear soon enough, I hope, how to create a persistence diagram where we can distinguish indeed non-isomorphic simple objects. So we all know this definition. So bottleneck distance can be defined classically, and the interleaving distance is just, given R index diagram and functors to a category C. We say that two of these are epsilon interleaved if there exists translation functor that map one to the other and allow those diagrams that I wrote there to commute. And we can prove for semi-simple abelian categories that stability holds in the classical sense. But more than that, we can prove what we call tightness. So basically, we can find equality between bottleneck and interleaving distance. But if our abelian category has essentially one simple object, and of course this is kind of a problem, because we would want to deal with semi-simple categories with more than one simple object, and we can indeed do that, and we can do that by defining a coloring. And so we introduced this concept of multicolor persistence, exactly to overcome the fact that, bottleneck distance, when we have many non-isomorphic simple objects, is really not informative, in that if we do not refine our space by introducing a labeling on the persistence diagram. So in a category, in a regular category with a rank, we can create now a family of ranked categories that will represent exactly our labeling, and they are described, the relationship between this R and R gamma are described by that functor C gamma, and that must be respectful of the two conditions that you see listed there. With these in mind, we indeed can create multicolored persistence diagrams. And it is interesting, I think it's an interesting remark, that these results was also recovered in a different flavor, not fully discussed, in this paper that was published in 2020. So what we have so far is that's great. We proved our equality between interleaving and bottleneck distance for semi-simple category, abelian categories with essentially one simple object. We introduce a coloring that allows us to distinguish between more than one simple object, and restricting that would preserve our equality, right? So what kind of examples can we build on that? Well, we can finally work on Levelpoint Clouds. So if we have graph, a weighted graph as the one in the top row on the left, and a coloring on his vertices, well, then we can build the filtration, and we can consider the poset of interaction of colors and interaction between colors. And now we can indeed write the diagram with all the interactions coming from all the different components of our posets. It should be, I should say that that category, the poset category, is not abelian. So how can we do that? Actually, we cheat, and we use a quotient. So by functoriality, we restrict ourselves to the poset where all the upper part is quotiented. And this allows us, nonetheless, to build that kind of diagram. And also this is detailed in the rank-based persistence paper. And you can see the difference with diagram that we obtain just considering cardinality. And so indeed, we can finally build this kind of persistence diagram where components are colored with the labels they correspond to. And another application that we can have is on manifold with a group acting there, like the one that I draw here. So we don't need to just analyze the quotient anymore of this space with persistence, but we can do that directly on the orbits. And again, we are able to describe the persistence diagram as the one that you are seeing on the rightmost part of the figure, and that preserves. So it doesn't only have corner lines, but you have corner lines with the group action that has not been forgotten. I hope the diagram is clear enough. You have to note that the minimum loop that is on the YZ axis, right? So is a fixed point by the action of Z2. So what we have then so far is that these multicolor persistence diagrams are nothing else, nothing more than the sum of the persistence diagrams of the components that we obtain and then just superimposed in different colors. Well, these ends somewhat my more theoretical part, and I hope that I more or less convinced you that, you know, we have indeed this axiomatic general framework that allow us to work with objects that are simply indexed by a real parameter, and you know, that still we can retrieve the properties that we want from this kind of construction. So we can build persistence diagram, we can compute bottleneck and interrelating distances. In some cases, we have equality between those two. And finally, that this multicolor persistence somewhat is a refinement, if you want, of the more classical framework, in which we can indeed distinguish, remember components that are coming from non-isomorphic simple objects. Let's now start with the applications. So as I told you, my main work revolves around machine learning and its mathematical interpretation. So this is the direction that I obviously chose. And to do that, I want to introduce very briefly what a neural network is. So the main component of a neural network is a neuron, is a computational unit, very simple, as the one you're seeing there, that substantially receives inputs, multiplies and sums input, multiplies these inputs by certain ways, sums them, adds a bias, and then applies a pointwise nonlinearity. And you know, these very easy computational units cannot do much, and indeed, it cannot solve a solved problem, for example. But if you stack a lot of them, then you indeed can. Even you get, and I think this is a very well-known fact, but what you get is that these architecture are universal function approximators. So what do we want to do with these networks and our framework? Well, my slide is not changing anymore. Sorry. Okay. So, you know, machine learning grew a lot in these years, and architectures, neural architecture, are no more of the kind that I showed you before, but they grew complex and complex. And so what we want to do is to try and use the framework we developed so far to represent how data, to try of making of these black boxes a bit more of crystal boxes, where we can understand how data are propagated to the network, how the network structures the data as a function of the task it is intended for, and how we can compare neural architectures. To give you an example of how complex and how hard to read these architectures are, you can see here the transformer architectures, and this is widely used today. And as you see, it's way more complex than a multi-layer perception that we saw before. So our dream application here is to have something so general that can be applied to any form of architectures, even the ones that are as complex as this one. Although today I'm gonna speak of way simpler ones. So the algorithm that underlies all our application is this following one. Oh, how pretty! Sorry, there's a child, a beautiful child. We start by selecting the data set. we define a model, and then we train it on our data set on a certain task, say a classification task. Then we evaluate our model on a test set. We retrieve the data set that it was embedded in a certain layer of our network. And then, we simply compute vectorial scripts, we remember our labeling, and we draw our persistence diagram. So in a schematic, it's something that looks like a bit like this. So we start with some images, for example, we vectorize them, we pass them through our model, and we apply the affinity I described it before, and then we end up with a Squashian linearity that allow us to classify what we see, and we test it, we remember the poset of the labels that we had, and then we build our output. Remembering, of course, from which element of the power set of the labels the cycle was coming from. I wrote these as in Python and Torch, and it looks a bit like that. Of course, the code will be public, and I hope that if someone is interested, will use it. It's very, very, very intuitive, I hope, even if you're not familiar with machine learning. So you can select a data set. In this case, all our examples are built on a NIST, which is a data set of handwritten digits. Well, you want to read the data and store your results. So you will give these folders. You will select our labels, all of them, or a subset. Then you will initialize the model simply as that. And you give some configuration for persistence. And finally, you will simply call this five functions that will give you the diagram. So now, what we can do with that? On the one hand, we can look at how data are distributed are encoded, if you want, by different layers of the network, and this is exactly what we did here. So as you can see, we drew the multicolor persistence diagram for the first layer L1 and the second layer L2. And as you can see there, what we get is that in the first layer is very much not easy to distinguish points that belong to, let me call singleton labels components, so pure label components if you want, and mixed ones. However, in the second layer, which is the one in the embedding, so we take the activation of the layer as embedding, there we can indeed say something. So mixed components are born late and have sort of higher persistence. And another thing that we can do is to see how our network behaves with different subsets of labels. So interesting, on the one hand, we find results that were similar to the one we saw before. Here I'm taking the last layer all the time and different sets of labels. And indeed, my not pure cycles always are born late. And somewhat have higher persistence than the rest. And I think that this is somewhat interesting, right? It tells us something about how this data, this is always H1, huh? How the data were encoded in this last layer of our network. And obviously, all the interface allows you to perform more intensive experiments. So it's as easy as, you know, selecting now sequences of architectures and sets of label subsets. And what you get when you do this, when you use this algorithm, is that, you know, all your model will be trainable. You have all the statistics on the test. We reduce the dimensionality of the embedding that you chose just to give it a look by eyes, and of course the persistence diagrams in a given degree. And so you obtain always something like that, where the matrix is the basically on the diagonal you have the recall. The dimensionality reduction shows you how, in this case, UMAP is seeing the embedding, and finally you have the persistence diagram. So this is the results that we obtained by considering two different architectures, one with a single hidden layer of 100 units, and the other with 4. And as you see, the two reductions, dimensionality reduction, do not look that different, that far apart. However, when we look at the persistence diagram, well, they are messy. The first row is pretty messy. There are a lot of labels, a lot of possible subsets. But what we did here was to select the most relevant corner points. And this is what we get. So we get indeed that these not pure cycles, and however, the points that are with high persistence in this case are exactly the ones of the labels that are basically causing troubles to our network. They're difficult to distinguish. I'm so sorry, I will not tell you how I did select these points because Massimo will talk exactly about that tomorrow. It's a very, very new algorithm that we're testing only these days. Of course, we can compute distances, right? So our multicolor bottleneck distance is simply the max of the distances between the diagrams that have comparable subsets of labels. And as you can see here, again, the distances, the way in which these two networks dealt with hardly distinguishable classes are very different for some of them, right? If it is easier given the MNIST structure to distinguish zeros and twos, it's very hard even for humans sometimes to distinguish 2 and 8. And there we see the maximum relative bottleneck distance. And of course, when you have a distance, well, then you can easily build clustering and classify your networks. So what I did here was simply to take, you know, models with 1 to 4 hidden layers of the same endowed with the same number of units and nonlinearities, and we have a sort of we have a clustering of these models. So we have indeed a distance. What you can note on this figure is that it doesn't seem to depend much on the accuracy. So if two models dealt, if you bought what I told you so far, if two models dealt with the data in a similar way, doesn't really mean that they have similar accuracy, which is, I thought, very interesting for us to explore. All of these applications, no, I'm lying, part of these applications are described in a paper that we published last year for a conference, statistic conference in Italy. I would like to discuss my last application. So what you saw so far, well, you know, was our multicolor persistence, and it was based, however, was based, you know, on homology and Vietoris Reefs. That is something that we are used to work with And I don't know, maybe someone could argue that we didn't need that big of a framework to do that. But we can also, sorry, use more exotic constructions such as blocks. So bear with me with these examples. It's a single slide and it's my last one, but it is indeed a bit complex. So I hope that some of you know reinforcement learning. If you don't, it is not really complex to have a shallow explanation of it, but what you have is an environment that in this case is represented by this maze shaped as a cross, and you have an agent that can interact with this environment, and at each state it will perform an action, and as a function of a reward that is given, it will optimize its policy so that given an event and a state, its action will allow to have a maximal reward. How you do RL algorithmically, classically you use Q-learning, so you're solving a system of equations, Bellman equations, but you can also use, you can use deep learning. You can have a network that optimizes its weights for the agents to choose the next action. And in this case, the task that I'm considering is very, very easy. It's a taxi cab task. So we have our cities that cross, made up of a few states, and we have a taxi that starts this journey. It gets an initiation that tells where the passenger is. It gets the passenger, and then it delivers the passenger with a with a series of action. And of course, if all these actions are correct, then it gets a reward, and otherwise it gets a negative one. So what can we do with that? Well, we can build a complete graph by considering all the states of our environment, and we can weight this graph. How do we do that? Well, in the case of neural networks, you can for what I did here was to take the activity of the neural network at each state given each action, and then I tried to regress the activity of one state to any other state, and these gave me the weights for each of the states. So basically what I'm wondering is the activity in state 1 a good predictor for the activity in state 2, and so on and so forth. Obviously, you can filter now this weighted graph, and we can consider blocks. We can build our persistence diagram, and each point will be linked. Each point, each corner point will host some of the states. And we can then map back the persistence diagram onto the maze by by associating each of the states to the block in which they are in, and that has maximal persistence. So if we do that with an optimal agent, so an agent that indeed completed successfully our task and that has an optimal policy, interestingly, this is what we get. So we get that all the states in which the agent is receiving a cue, so those are the outermost states 1, 6, 5, and 9, are very relevant, has high persistence. Corridors have low persistence, are all identified together, and the center, as where we take the decision, has again high persistence. So this is the kind of representation that we can get by considering these kind of constructions. And with this, I hope that I convinced you that that we can indeed use this kind of generalized framework that is not that abstract. And in the future, of course, we would like to use actively this framework during active learning with neural networks to try and find on the fly examples that are very, very different. Adversarial examples is what we call, so examples that are critical for the network, that are not solved well by the network. Of course, compare model and compare agents in reinforcement learning. And with that, I think my time is almost up. So I thank you.
Thank you very much, Mattia, for your beautiful talk. Very clear. As always, send me a cue in the chat if you have a question. In the meantime, I'm wondering, do you have an elementary question that motivates you in the formation of this framework? I guess what I'm imagining is try to think of somebody who is not fluent in category theory and motivate what you did. Because if you first introduce category theory language, it's unclear, possibly, what you're really doing.
That's very, very true. And I have to say very, very on point, even because it was very, very hard to write this paper and then even pass the message, actually. And it's still hard. Now, hopefully I wasn't clear enough, but I think the main aim and the basic idea is really due to Massimo again. And his idea is really, let's build interesting stuff directly on graphs and without needing any auxiliary construction, right? So this is what
there got to be one elementary question that is a simple version of this framework where you don't use topology. No?
Well, in my head, I always use this last block construction to
Okay.
as an example. But you know, for example, click communities also are very much used. They don't really need to be passed through simplicial complexes to be studied, actually.
Are strongly connected components in directed graphs an example that would fall into this framework?
Yeah, actually, this was one of the things that Alessandro Mella studied in his thesis. Absolutely. We didn't have very conclusive results there, but yes, it did do that. Also, was something that interested me about his studies was the on random graphs, right? So to see which variation I mean, is there a mother persistence diagram that we can link to random graphs to understand its basic features, right? And then this could be applied to small world-like network or things like that, and it would be very, very interesting. And again, I'm borrowing ideas from Massimo, I have to admit.
Okay, thank you.
Thank you very much.
Kaylin has a question, and then Wojciech.
Yeah, thank you. So very interesting talk. So you mentioned a little bit about the group actions, the symmetry things, and it can be like imposed in the persistent the graph. So can you say a little bit more about that?
I'm very sorry. I really didn't hear you properly. You're hinting at the group action, right?
Yes.
Okay. Let me just go back to this.
Yeah, you have an example. I think you just like a symmetric situation, and then you said that one can be embedded into this one. Yeah. So if we have a more complicated group action, this one can also be somehow embedded into this labeling.
Well, you got me, right? This is very easy. This is really a toy example that we built. So, well, no, I believe that if you have orbit, you can do that. I wouldn't see a reason why you could not do that. But I never wrote an algorithm to do this. Never did. And I think it would not be that easy, luckily. You need some compatibility, right? Because otherwise you risk to have to take a sort of mean on the orbit. Yeah. This is also discussed in the paper I mentioned before. It's discussed in detail. So I invite you to read it there, and then of course come back to me or Pietro if you have any questions. More than welcome.
Thank you, thank you. Yeah, the reason
No,
I'm
thank
asking
you.
that is that the many in the materials, a lot of like a crystal group structures, and they are very useful in characterizing this kind of material things. Yeah, I will definitely read your paper and naturally have more questions. Yeah, thank you.
Well, I would also thank you. Thank you so much.
Wojciech, you had a question.
Yeah, so it was also related to group actions. So you are looking for the, you look at these representations, which would be semi-simple, right? So that puts some restrictions on which representations you are going to look for, right?
Definitely.
Typically, it would be like, probably you look at finite groups, but then the field, the characters of the field should not divide the order of the.
Absolutely, absolutely. Again, all these details are discussed a bit in
right.
the paper.
Right, but now my question is: Have you looked at that? Have you like faced an interesting example of some an interesting group, except like maybe rotational action? Okay, like something which is not abelian. Let me put it this way.
I love the question, and well, we were planning to do so, or we were planning to do so. So yeah, as you said, you need to restrict a lot to do this kind of construction. That for sure.
But what I would like to sort of say is that are there, I'm curious about examples, natural examples where, for example, the action of sigma 3, okay, so the plays a role, right?
Yeah, I agree.
Rotational, translational symmetries, these are often has to do with images, but things like that. So maybe what Shah asked before, maybe some materials, crystals, they have interesting maybe symmetries.
I think that for sure we should dig into this, even because actually even on continuous actions, it relates a lot with that other work that I did in the past with Patricio Frozen about how to use this kind of equivariance in persistence, right? However, we never built an example like that.
Yeah. But now, do you have an algorithm to actually decompose these persistent modules, like efficient algorithm?
No.
I mean, this I guess maybe it relates to Francesco Vaccarino's talk.
I don't know. I mean, I have an algorithm. It's not efficient, right?
Yeah, exactly. Okay.
It's
existing algorithm. Yeah. Okay.
Yeah, it's very, very much brute. But yeah, I think we should. I would like to be very honest with all of you. This work is going very slowly and is a bit deadish. And with this conference, I really found again the will to go on, and maybe I will convince also Pietro to tag along with me. And of course, any of you, if you want to, I would be more than happy. And I agree that it would be super interesting, even in the study of orbitals, right? That would be so cute. There was a very nice paper about mathematics and music that was taking advantage of orbitals a lot some years ago. And I would very much like to learn more about those kind of actions, but I didn't have any examples.
Thank you.
Well, thank you.